All right, welcome back. We're now in section 8. We're making our way up the stack, if you will. We just did the network layer in our model. Now we're moving up to the transport layer. In this section, we're also going to talk about some of the application layer functions as well. We don't really get into a whole lot of different applications. We focus most of our attention on some of the key applications that exist in networks today that allow clients to communicate, stuff like DHCP, DNS, and so on. But we're finishing up our discussion of the stack by talking about TCP, talking about different critical applications. We'll, of course, talk about UDP as well in this section so that we can get a good understanding of how these protocols function. We're going to break down these protocols just like we did with IP. We're going to look at the headers. We're going to identify what the fields of the headers are for. For example, what is a port number field? What is a sequence number field? Acknowledgement number field? A window size, etc. We'll break that down, and then we'll take a look at some of the applications that are critical to network communication. So again, and this is with regard to the enterprise architecture model. We're now focusing on application layer information as well as the transport layer. That's going to include two specific protocols, TCP and UDP. All right. So let's start by looking at the transport layer protocols. Specifically in this case, we're talking about TCP and UDP. There is a significant difference between these two protocols. One has a whole bunch of reliability mechanisms built into it. It's got sequencing and it's got acknowledgments. It's got flow control mechanisms. There's various flags that we have available to us as well to be able to identify specific TCP-based transactions, whereas UDP doesn't have any of those things. It's a unreliable, basically flow-based protocol, much like IP, with no sequencing, no acknowledgments, no reliability built into it, and so on. So what are the responsibilities primarily of the transport layer? It says here session multiplexing. And that's actually pretty important if you think about it. Let me go back to my paint here, and I'll explain what they mean by specifically by session multiplexing. Okay, let's see here. So let's say I've got my PC here. This PC is running a multitude of applications. It's running maybe some sort of VoIP application. Maybe it's running some sort of database application. Maybe it's running some sort of web application. Maybe we're also running some sort of email application or whatever it might be. Each one of these applications are competing for the network resources. Specifically, they're competing to be able to communicate out to the rest of the network. Session multiplexing is the idea where we take all of these communication channels, all these individual protocols, and we interleave messages from each of these protocols and kind of mix and match, if you will, the segments for those protocols rather than sending all of my email data at once or sending all my VoIP data at once or all my database traffic data at once. I'm multiplexing the use of that circuit, and everybody's kind of getting equal access, somewhat equal access. It's not perfectly equal, but equal access to those network resources. So that's what they mean by session multiplexing in this particular case. The identification of different applications. The way we identify different applications at the transport layer is how? How do you think we identify different applications at the transport layer? With port numbers. Port numbers allow us to identify applications. So we're going to talk about what those port numbers are and specifically how those port numbers allow us to identify not only the individual application, but even different sessions of a particular application. So that's going to be something we'll talk about here. Segmentation, we talked about that briefly in our previous section. That's where the maximum segment size concept comes into play, where the clients will negotiate what the maximum data payload is at layer 4, what we call a segment. And that's done typically in the three-way handshake. We have flow control mechanisms. The protocol is connection-oriented, meaning that we have sequencing and acknowledgments that take place. I send you packet or segment XYZ, you acknowledge the receipt of segment XYZ, and so on. All right? Those, by the way, have an asterisk next to them because UDP doesn't do those things, only TCP does. So when the application calls for it, when it's required, we're going to write the application to use TCP. If it's not necessary, if we don't need those features, then we're going to basically use UDP as our transport protocol, which is very common, by the way. A lot of protocols are designed to run over UDP because they can't take advantage of those mechanisms that would be built into TCP. All right, so let's break down some of these concepts. Session multiplexing is the first one. And like I said, we have different types of applications. This diagram is really kind of just identifying maybe two transports, UDP and TCP, but let's assume those 1 and 2 are not different transports. They happen to be different transports, but they're also different applications. All right, so 1 represents maybe my email application, and 2 represents my voice over IP application, because voice over IP is typically transported over UDP. All right, so we encapsulate the data inside of the transport layer protocol, which is, of course, going to include the IP routing piece as well. And then over that data link, we're intermingling or commingling segments from one data stream with segments from another data stream. The idea here is that we're trying to give equal access to that bandwidth and to that network resource by multiplexing those sessions, rather than saying, okay, this traffic is always going to be processed first, this traffic is processed second, and so on. All right. Identifying applications, like I said, we identify applications based on the port number. We'll get into the port number concept a little bit later on. Applications are identified based on port number, not only source port, but destination port. All right, if you think about it, what if I had a scenario like this, where I've got a PC, all right? I've got a PC here talking to a web server here. And we'll even make it simple. We'll say they're in the same subnet. So here's the PC, here's the web server, okay? And these guys are on the same subnet. When I look at the PDU, we have our source MAC, we have our destination MAC, we have our source IP, we have a destination IP, we have a source port, and we have a destination port, okay? Layer 2, Layer 3, Layer 4. The addressing components are what we use to identify the application, to identify the destination host, and so on. I open up my browser. Let's say this is Edge, IE, right, Edge, and I go to the web server. Source MAC is the PC, destination MAC is web, source IP is the PC, destination IP is the web. Source port is some sort of random ephemeral port, so 3192, and the destination port is 80 for HTTP traffic. And then I open up another browser, Firefox, and I go to the same server. Guess what? Almost all of this information is the same, isn't it? It's still the same source MAC, it's still the same destination MAC, it's still the same source IP, it's still the same destination IP, it's still the same destination port. But what is unique is the source port. This one component is what allows us to uniquely identify where the data flows to the application. That ephemeral random source port. So when the web server is responding, it's going to respond to port 3199. This PC knows that's supposed to go to Firefox, or it's going to respond to 3192, which is supposed to go to Edge. Does that make sense? So when they say identifying applications, that's what they're referencing in this particular case. Yes, we do have port numbers that are assigned to well-known applications. So we have like port 80 is HTTP, and port 22 is SCP or SSH, port 23 is Telnet, etc. But we also identify applications based on the higher port numbers as well. It's not just those low, well-known port numbers. So the port numbers are very important for us to be able to identify the application. All right. The next thing we mentioned here was segmentation, based on identifying the proper size of the datagram. Right? It says here TCP takes variable-sized data chunks from the application layer and prepares them for transport onto the network. The application relies on TCP to make sure that each chunk is broken up into smaller segments that will fit based on the MTU for the network layer. All right? It's a little bit misleading because it makes it appear as though MTU is something that is related to layer 4 when actually it's MSS, maximum segment size. I will show you that in a Wireshark capture a little bit later on. But the general concept still applies. We're taking large amounts of data, we're dividing them into smaller pieces so that we can ensure that data gets processed and over the network without having to be fragmented. What is the reason to divide data up in the first place? Why is it important to divide data up at all? Why do we care? Why can't I just send a 100 meg file in one datagram? Because if I do that, if I allow those large datagrams, eventually the large traffic is going to starve out the small traffic, right? If you think about it, most of our applications are competing for resources on the network. I've got my PC here sending data. If I'm sending a 100 meg file, eventually I'm going to get to a router that has an interface that needs to process that 100 megs. Well, if that 100 megs hasn't been divided up, it takes time to put that data onto the wire and propagate that data. Well, guess what happens to my 12 kilobyte file, right? Or my 60 kilobyte file, or my 100 kilobyte file. It has to sit there and wait while that 100 megs is processed, okay? Which literally could take seconds. So in order to ensure that we have kind of more of an even playing field where the protocols are kind of all treated equally or treated the same, we demand that the data be divided up into smaller pieces. Yes, that adds more overhead. Why is there more overhead if I'm dividing data up into smaller pieces? Because all that data has to be encapsulated. You have to have headers, right? If I take this 100 meg file and I break it up into 50 pieces, I now have 50 IP headers, I have 50 TCP headers, or whatever, because each of those individual segments need to be routed and switched independently. But quite frankly, networking today wouldn't work without the requirement to divide data up into smaller pieces. Just wouldn't work because we have so many different requirements for different applications. Okay? Flow control, I'll get into this in more detail in the concept of windowing and buffering and retransmission. But flow control provides us a way of throttling back or speeding up communication by adjusting variables within the communication path, right? Or at least variables with the data itself. They don't really get into specifics in this particular paragraph here, but I'm going to show you what those specifics look like when we get into our Wireshark capture and we start to look at these datagrams or these segments in Wireshark. All right? TCP Flow Control really just provides me the ability to speed up or slow down communication, right? I'm an individual client, but I might be talking to a web server. That web server might be servicing hundreds and hundreds of clients. So just because I have all the resources and bandwidth and CPU cycles available to process data doesn't mean that the device that I'm communicating to is going to have all those available resources. So flow control allows us to control the speed of delivery, the amount of information that's being sent back and forth between the sender and receiver. Okay? All right. So what is a connection-oriented protocol? TCP is an example of a connection-oriented protocol. There are other types of connection-oriented protocols, but TCP is kind of the classic one that everybody references when we talk about connection orientation. The concept of connection orientation means that there is some sort of negotiation of the channel of the communication stream prior to sending and receiving data. Now, in the form of TCP, this occurs as a three-way handshake. And again, we'll break down. I'm going to show you guys what a TCP handshake looks like in Wireshark. We're going to break that down. But there are three main objectives to connection orientation. Number one, we have to establish the communication channel, which includes also establishing the parameters of that communication channel. Things like what are our initial sequence numbers? What port numbers are we using for this communication channel? What size of window do we have? What are the options? Let me show you real quick since I kind of spilled the beans a little bit there. When I go back to here, this is the connection orientation process that we see here. Let me kind of move this down here. You see this Syn Ack? This is what we call the session establishment phase. And I'll get into the details in a little bit here, but if I look at the Syn, I pull up this initial Syn packet or segment, you'll see that with regard to the connection, we are negotiating all of these variables. What is the maximum segment size? What window scaling factor am I using? What is the window size? What are my initial sequence numbers? And so on. What are my port numbers? Source and destination port, 7036 to 7777. So all of this stuff is being negotiated. Now, that's not to say that UDP, which is a connectionless protocol, doesn't have at least some function, right? UDP does identify port numbers, but UDP doesn't do segmentation. It doesn't define. When we look at a UDP header, you won't see things like sequencing and acknowledgments. You won't see window size. You won't see those kinds of things. All right? The second thing that the connection-oriented protocol does is it allows us a way to identify the order of the data. And that is done, by the way, by this particular field right here called the sequence number. The sequence number allows me to identify what the order is of the segments as they arrive at the receiving host. It is entirely possible that I send you 100 segments or 200 segments, and either some of those segments have to be retransmitted, or some of the segments just simply arrive out of order because they took a different path or they took a different approach to get to the destination. All right, so the sequencing is a critical piece because it allows me to take that data, store that data into memory, store that data into a buffer, and then once I've received the data, I can then sequence it back in order, compile it back together, send it up to the application so that the application can process that information. All right? What is the downside to all of this reliability? Overhead, absolutely. A TCP header is 20 bytes. By a minimum 20 bytes. It actually can be even larger than 20 bytes. In fact, in this particular capture, this TCP header is, if we look at it, we've got a total length field of 52 bytes, and our IP header is 20 bytes, which means we actually have 32 bytes of information that we're carrying. Well, that's the size of this header. This TCP header is 32 bytes. Because we've got our 20 bytes, but then we also have 12 bytes of options. 20 plus 12 is 32. It's amazing how all these numbers kind of work out when you know what you're looking for, right? So we actually have 12 bytes of options here, which means that we're not using a standard TCP header. A UDP header, 8 bytes. Always 8 bytes. Doesn't change. The UDP payload is not variable in length, it's fixed in length. Okay? So yes, there is a trade-off. To have that reliability, we have to have that overhead. Some applications require that. Other applications don't. For example, if I'm doing voice over IP, like real-time voice over IP, how could I take advantage of those reliability mechanisms if I want to have a segment retransmitted? In order for me to have a segment retransmitted, I would have to buffer or store the other segments that aren't being retransmitted, which means I have to delay the playout or delay the delivery of those datagrams to the application. Well, that's not going to make for a very good conversation if I'm delaying the delivery of the data. So because real-time applications like voice over IP and video over IP can't take advantage of those characteristics, we simply don't use them. We don't use TCP as our transport. There's no reason in having the overhead if I can't take advantage of what the overhead provides. So we're talking about reliability versus best effort. TCP has all that reliability built in. It's a connection-oriented protocol. It does sequencing, it does acknowledgments, it does window size, it does flow control, it does all those things, whereas UDP is completely connectionless and doesn't do any of those things. And like I said, some of the most common types of applications that use UDP, real-time voice, real-time video, and there's other protocols. Snmp, for example, is a UDP-based protocol. Tftp, Trivial File Transfer Protocol. DNS port 53 for, like I said, for client-based transactions, not server-based transactions, but client-based transactions. All right? So what is this connection orientation? Let's take a look at this in our Wireshark capture in the form of a Syn Ack process. All right? Here's the way that the kind of analogy that I use to describe this three-way handshake. A phone call, right? Let's say that I call your phone and you pick up. I say, hey, this is Scott, how are you doing? You say, oh, I'm doing great, how are you? Hey man, let me tell you this story. Okay, that's connection establishment. That's oriented connection or oriented communication. You've acknowledged that you want to talk to me. I've acknowledged that I want to send you information, and I can start sending my conversation. And then throughout the conversation, you're going to use words to indicate that you're listening and you're understanding the message, right? You're going to say, oh yeah, really? Yeah, really? Those are like little acknowledgments that you're receiving the information. Imagine if you had a conversation, UDP, I have placed a phone call, you pick up, and I just start talking. And you don't say anything, and then I hang up. That's UDP. I have no idea if I was talking to the right person. I don't know if you were ready for the message. Yeah, you didn't. Yeah, exactly. It's kind of like saying, you know, I tell you this joke about UDP, but you might not get it and probably don't even care, right? But that is the joke, obviously. But yeah, it's not a very good joke. But anyway, there is a... All right, so let's take a look at this three-way handshake in Wireshark and kind of take a look at what it looks like. And again, the way that I found this, by the way, I captured a bunch of datagrams in Wireshark. I've got 974 packets that I captured here. And let me take out the filter. Wireshark does something very nice for us. It creates something called a stream index for the datagrams that you capture. And it's something that's not part of the TCP header, but it gets added to the Wireshark capture. We can see stream index 2 here. I can apply a filter based on that index. And this is the entire conversation, at least the part that I captured. So that was one conversation. This is number 3 is another conversation. Number 4 is another conversation. Number 5 is a different conversation, and so on. So you can see there's several different TCP flows that I captured. But if we look at this particular flow, we can see the three-way handshake happening here. Let's open up the first one and take a look at what we're actually supposed to see here with regard to TCP. There's our layer 2 header. There's our layer 3 header. Here's our transport header. The source port is 7037. The destination port is 7777. Now you might look at that and say, well, that's not really a well-known port, but that does fall within the registered port range. That falls within the registered port range. We'll talk about that a little bit later on. Okay, so we are establishing the source and destination port. Remember what I said about the brackets, the square brackets? What did I say about that with regard to Wireshark? This is not part of the TCP header. This is something that Wireshark is adding for your analysis, for your benefit. So yes, source port is the first field in the TCP header. Destination port is the next field in the TCP header. Sequence number, raw sequence number, so this is kind of a negotiated sequence number. And then next sequence number, again, that's in brackets, so that's added by Wireshark, and then acknowledgement number. We'll talk more about sequencing and acknowledgement in a little bit. That's not the point of this particular conversation. So what we're looking at, though, are, here's the header length. So there is a header length field, 32 bytes. But we're looking specifically at the flag fields here, right? These flags represent different types of TCP transactions. This happens to be a synchronization transaction, meaning I'm trying to establish a session with you, so the syn flag is set to on. Meaning I'm sending you this TCP segment and I'm saying, hey, I want to communicate to you on port 7777. Now, if that device has port 7777 open and can respond, has the resources to respond, it will respond. If the device doesn't have 7777 open, it's going to respond with a TCP reset saying, I'm not listening on port 7777, so go away, right? That's how scanning tools work. A network scanning tool basically just sends SYN requests on different port numbers, and if I get a Syn Ack, I know that that port is open on that particular device, okay? By the way, that's also how a TCP SYN flood attack works. A TCP SYN flood attack is a denial of service attack where you just send a whole bunch of SYN requests that causes the device to send a bunch of Syn Acks, but I never established the session. Now I have all these half-open connections, and I use up all the resources on the device because of all these half-open connections. All right? But so the TCP header is actually a pretty complicated header. There's a lot of different fields here. And again, that's because of all that reliability stuff that we have to have. We've identified a window size. We have a window scaling factor of 8, so let's skip that for now. Let's say that the window size is 64,240. By the way, this field is 16 bits, so mathematically that field can only go up to 535 anyway. The window size, probably shouldn't talk about it now because it's not really part of the three-way handshake, but I'll mention what it is anyway. It defines the amount of data that I can send before I expect to receive an acknowledgement. It doesn't define how much data I can send in one segment, but it defines how many bytes I can send, however many segments that might be. We negotiated a segment size of 1460. So if I take 64,240 and divide that by 1460, that means I could send you 44 segments before you send me an acknowledgement. Okay? That's to reduce the amount of traffic generated by TCP. If I required you to acknowledge every single segment I sent you, then we would be constantly sending data back and forth. This window size will adjust. It'll go up as we send more and more data successfully without any lost segments. And if we lose a segment, it goes down because the connection is not as reliable and we need more acknowledgements. The only reason I'm talking about it is because this is a variable value. This is not a fixed value. And it also doesn't have to match on both sides. This particular device says you can send me 64,240 bytes of data at 1,460 bytes. We'll see what the Syn Ack says in a minute. And by the way, it's actually a larger window size because they applied a scaling factor of 8. So actually the window size in this particular case is 64,240 times 8. And then if I divide that by the maximum segment size, 352 segments can be sent without an acknowledgement. Okay? So sometimes the scaling factor is applied, sometimes it's not. They have the scaling factor because networks have become more and more reliable, which means that we should be able to send more and more segments without having to get an acknowledgement. It's just to kind of make TCP more efficient. All right, and then we're negotiating some other parameters of the TCP session. SACs are permitted. We don't need to get into all the details of this, but segment size, that's a big one, right? How much data can I encapsulate inside of one TCP segment? All right, so this is the Syn. Now let's look at the Syn Ack. Notice on the Syn Ack, the ports reverse. The source port becomes 7777, and the destination port becomes 7037 because this is the acknowledgement. Also notice that I set the acknowledgement number to 1. All right. Actually, the raw acknowledgement numbers are more random, but the actual the relative acknowledgement number is 1. But look what flags are set, the Syn flag and the Ack flag. Ack meaning acknowledgement. Notice this device said, my window size is 5840 with no scaling factor. The window scale is 2. Well, not 8. Actually, 256 was one I saw previously. But so this particular device is maybe more busy, maybe doesn't have as many CPU cycles available, or whatever. It's negotiating different parameters for the session. And then I get the final acknowledgement. This is coming back from the original source, saying, okay, I acknowledge that. Notice also that the window size changed again. Now the window size is 513, but we still have our scaling factor of 256. I said it was 8 before, but 8 was the value, which resulted in a multiple of 256. So 131,328 bytes of data divided by 1460. It's kind of funny because those numbers always kind of work out, right? 131,328 divided by 1460. So that's about 90 segments. It should have actually, I guess not. I thought it was always going to be a divisible, a whole integer. Let me make sure I did it right. 328 divided by 1460. Yeah, not in this case. I always thought it was a whole integer. Every time I've done that calculation, it's always been kind of a whole number. But in any event, it doesn't really matter. It just defines how much data can be sent before an acknowledgement is required. All right, but notice in this final acknowledgement, we've got a standard TCP header now. So the options were only used initially to negotiate the parameters of the session. And then once the session is established, then we can start to send and receive our data. All right, this is like a three-way handshake. Well, not like, it is the three-way handshake. And that's what TCP does in order to establish a session. Some people call it the Syn Ack process. The sequencing and acknowledgments are negotiated as well, but that's the three-way handshake. Okay. Conversely, there's also a graceful close option too with the fin flag. The fin is for finish, which allows us to shut down a session as well. All right. Once the connection is established, we can then go through and adjust certain values. We can adjust things like the window size. Sequencing and acknowledgement is just going to continually increment based on the amount of data that's being sent back and forth. If the book doesn't talk about that, I'll show you guys how we can recognize that incrementing of sequence numbers and acknowledgement numbers. Actually, they do mention it here, so let's take a look at it. Because they do say the receiver responds with an acknowledgement number that is equal to the next expected sequence number. So let's take a look at what that means in the case of sending the data. So let's say, let me find a better conversation because that one's a little bit anemic. Most of these, I didn't really capture a whole lot of data. Here we go. This is a kind of an extensive conversation. It's kind of in the middle of the conversation, but if you look here, the sequence number in this case is 1. Actually, so we just started this conversation, but the next sequence number is 182. How was that calculated? Look at the amount of data that is contained in the payload. We have 221 bytes of data, right? This is from the packet header. Minus this, so we've got 221 minus the IP header. So there's 201 bytes of data in the TCP payload, including the TCP header. The TCP header is also 20 bytes. So if I take 201 minus 20, 181. So the sequence number is relative to the amount of data that's being sent. I can tell from the relative sequence numbers, not the raw ones, but the relative sequence numbers, I can tell how much data is actually being processed. 181 bytes of data. Look what the acknowledgement is coming back from the client. I acknowledge, go back here, the acknowledgement number is 182. I always acknowledge the next byte of data I expect to receive. So if I look at the next segment, here, total length is 125 bytes. Again, we would subtract the 20 byte header here, so that's 105 bytes. And we would also subtract the header here, which is another 20 bytes. But you can actually just calculate it from here. Here's the sequence number. Here's the next sequence number. 267 minus 182 is 85 bytes of data. Add 20 for the TCP header. Add 20 for the IP header. That's 125 bytes of data. Total length field is 125 bytes. See how that works out? So these are all very, very predictable transactional events that take place. And if you understand how the protocol works, you can see the progression of data flow in a particular stream based on your understanding of how the protocol works. So what do you expect my next acknowledgement is going to be? Given that this is, my next sequence number is 267, I'm going to acknowledge 268, right? And actually acknowledge 267 because the first one was inclusive, right? So we have to include the first number, the initial number. So I'm acknowledging 267, which is the next byte. And it can kind of go through here. Now you can see in this particular case, our window size is relatively small in this transaction because we're not seeing data, and acknowledgement. We're seeing data, acknowledgement, data, acknowledgement, data, acknowledgement, data, acknowledgement. So that tells me that this was a session or a flow that was negotiated with a relatively small window size. All right, let's see if it actually is relevant, is correct. Yeah, the window size is only 2,400 bytes, which is basically one segment, right? Because if I take 2473 and I divide it by 1460, which is a typical segment size, it's 1.6, but you can't send a sixth of a segment, so you have to acknowledge every segment. So that's what we're seeing in this case. Some other flows, you might not see that. Other flows, you might see, let me go to flow number 4, flow number 3. Nope, that's a bunch of acknowledgements. Let's try flow number 2. Yeah, I didn't capture enough. Here's the where we're closing the session with the fin flag. Fin means finish the session. And then we're acknowledging that we're finishing the session. I really didn't capture that many datagrams here, so I'm not seeing, very large conversations here. All right. All right. Now, best effort, of course, none of that happens. In best effort, let me grab a UDP segment here. So let's clear the filter here. And because I now know what I'm looking for, all I have to do is go to the I already picked a UDP. I was going to say all I have to do is go to the protocol field and filter on protocol 17, and I'll get all my UDP segments, but I just happen to pick one, so we don't have to do that. But look at the UDP header. Source port, destination port, length, checksum. That's it. The brackets, again, that's added by Wireshark. Source port, destination port, length, and checksum. 4 fields. No windowing, no flags, no acknowledgement, no sequence, none of that stuff. All right? So UDP is considered unreliable. It doesn't necessarily mean that the application that's using UDP is unreliable, because a lot of times they will build in those options in the application. For example, RTP, the real-time protocol, which is used to transport voice and video, it has sequencing and acknowledgements built into it as an application. Even though it rides on top of UDP, it still has that functionality built into the protocol. All right? And they go through the analogy. I like the visual references that we looked at earlier. The analogy they often use is like a registered letter versus just putting a stamp on an envelope and sending it. You have no idea that it was received. You don't have any idea what day it was received and so on. That gives you an idea. All right? All right, so taking a look at the TCP characteristics, we've already pretty much discussed most of this, right? TCP operates at the transport layer of the TCP IP stack, layer 4. TCP provides application access to the internet layer, OSI layer 3, meaning that TCP rides directly on top of the network layer or the internet layer. All right, we also looked at all the different characteristics. It's connection oriented. It provides error checking in the form of a checksum. We established two-way communication, which is called a virtual circuit, by the way, but we established that two-way communication by doing the three-way handshake. TCP segments are numbered and sequenced. We just talked about that, about how those sequence numbers are created and the acknowledgments are created. And then upon the receipt of different TCP segments, we'll acknowledge that based on the actual byte count and the number of bytes that are being sent and received. And then TCP also provides for mechanisms for flow control. The primary flow control mechanism would be the window size. And again, here is our TCP header, a 16-bit source port field, 16-bit destination port field, sequence number, acknowledgement number, which are 32 bits, header length field, some reserved bits, and then we have our flag fields, which is our SYN, our FIN, our push flag, ACK flag, urgent flag, congestion window reduced, explicit congestion flag. We didn't get into each of the individual flags specifically, but we did talk about some of them, right? The window size we did talk about. Checksum. The checksum at layer 4, just like the checksum at layer 3, provides integrity checking of the TCP flow. And then we have our options, and we saw what some of the options might be, like window scaling factor, adjusting the MSS, the maximum segment size, and so on. And then the data field is just our payload. One thing that we didn't talk about are the port numbers. All right, so let's take a look at that real quick. TCP/UDP port numbers. It is a 16-bit field, which means that it goes from 0 to 65,535. But these port numbers, this range of ports, is actually broken up into three different sections. Let me see if I can find the right graphic. There's one specifically that I'm looking for. We have what's called the well-known range, and then we have the registered range, and then we have the unregistered range, or what we call the ephemeral port range. Let's do ports, well-known, registered, and that should pull up port number, well-known, registered, and that should pull up the one that I'm looking for right here. All right? So the ranges are here. 0 to 1023 is our well-known range, what we call contact ports. These are ports that are assigned to protocols that we use all the time. Kind of some of the most common protocols that you'll see today in networking. HTTP, HTTPS, DNS, FTP, Telnet, etc. Some of these ports you will have to be familiar with, but most of you are probably going to be familiar with these ports anyway. Things like Telnet and FTP. FTP is TCP port 20 and 21. Telnet is port 23 TCP. DNS is port 53, both TCP and UDP. The Snmp port 161, and so on, right? Some of the common ports: HTTPS port 443, HTTP port 80, SSH port 22, and so on. So you can get that whole list. Guess who manages that range, that number, those numbers? The IANA. All right. What happened, though, is that over time, they ran out of contact ports because there were so many applications that were developed, and these application vendors wanted to make sure, that they had specific ports that they were using for their applications. So they came up with this extended range of contact ports called registered ports. These are ports that could be used as ephemeral source ports, random source ports, but they're also registered to specific applications, like RDP, for example, right? Remote desktop. That's going to be 3049 or something like that. 3095. I can't remember RDP port number specifically what it is. 3389. I knew it was in the 3000 range. It wasn't really that close, but 3389. So even though 3389 can be used as a source port, as a random ephemeral source port, it also is registered to Windows RDP as a registered port. And then 49,152 all the way up to 65,535. These are our dynamic ports, what we tend to refer to as ephemeral ports. Ephemeral, E-P-H-E-M-O-R-A-L. I think that's how you spell it, or E-R-A-L. But ephemeral means just basically temporary. So dynamically temporary used ports. And again, we talked about the reason why we would have to have these unique ports for this communication. Okay? So the book kind of breaks it down, the header itself, source port, destination port, sequence and acknowledgement, used for reliability and congestion avoidance, header length field, reserved bits, the flag fields, the nonce sum enables the receiver to demonstrate to the sender that the segments are being acknowledged. A nonce is something that is used once. So that's what the term nonce actually literally means. But it doesn't really matter in this case. It's not something that we typically talk about. Congestion window reduced acknowledges that there was congestion, indicating congestion indication, saying that there is congestion. So I'm saying, okay, I acknowledge that there's congestion. I'm going to go ahead and reduce my window size because I don't want to start losing segments. Explicit congestion notification, which is the extended, indication that congestion is occurring, which means that segments are either being delayed or being dropped. Urgent, the data should be prioritized over other data. The ACK used for acknowledgement. A push, PSH flag, means that the application data should be transmitted immediately. That means that, hey, even if data arrives out of order, even if you get sequence number 1, and then you get sequence number 3, and then you get sequence number 2, and then you get sequence number 5, don't wait for sequence number 4. Just send the data up to the application without waiting or delaying that information so that the application can process that data immediately. A TCP reset is how we indicate that a TCP session should be reset. The Syn flag is to synchronize, establish a session and synchronize the sequence numbers, and the fin flag means that we're going to close a particular TCP session. We don't have any more data to send, so we want to gracefully close the TCP session. Window size used for flow control. We talked about how the window size is used to identify flow control. The checksum used to validate the integrity of the TCP data and payload. It's a CRC, cyclic redundancy check, a 16-bit cyclic redundancy check in this case. Urgent pointer is a flag that's set. It's essentially an offset value for sequencing, meaning that we're sending you urgent data. It needs to be processed in a special way. And then options, we saw anywhere from 0 to 320 bits, options that allow us to specify things like what is the maximum segment size, what is the window scaling factor, and there are other options for TCP. These aren't the only options that are available, but we don't need to get into the specifics of that either. That's really, actually, I would say it's not even something that we would limit to an advanced routing class, because it doesn't really matter. I mean, routers don't care about TCP, switches don't care about TCP. We're only learning about TCP because it is a fundamental part of the protocol stack, and it's a way that we communicate. All right? UDP, very simple. Obviously operates at the transport layer, but UDP doesn't do any of those things, right? UDP operates at the transport layer. It provides applications with access to layer 3, just like TCP does, but it is a connectionless protocol, basically one-way data flow, meaning I send you data, but I don't get an acknowledgement. There's no advanced notification that data is being sent, so there's no three-way handshake. We just send the data. If it gets there, it gets there. If it doesn't, it doesn't. If you're ready to receive it, you're ready. If you're not ready, we don't care. We're sending it anyway. All right? There is limited error checking. We do have a checksum value in the UDP header, just like we do in the TCP header, but there is no concept of acknowledgement or even retransmission. If a segment is lost or a segment is discarded because the checksum fails, I don't notify the sender that I've discarded a segment because of a failed checksum. Then we have to rely at the application layer. We have to rely on the application to be able to recover from that error. All right? So no error recovery, very, very lightweight protocol. The header itself is only 8 bytes. It's fixed in size, so it's a significantly smaller header than TCP, actually almost 3 times smaller than the TCP header, right? TCP header has a minimum size of 20 bytes, and it can go even higher than that with the options. So we have a source port, we have a destination port, we have a length field, which allows us to identify the header length plus the data, and then we have a checksum field. That's pretty much it. Okay? All right. What about the application layer? Obviously, we could spend a week just talking about applications. There are thousands and thousands of applications, probably hundreds of thousands of applications. But the applications that we focus on in this class are applications that we tend to use in relation to network devices. Things like management protocols, like FTP for file management, SSH for remote access, Telnet for remote access, HTTP for remote access, and so on. FTP, the file transfer protocol, actually uses 2 TCP port numbers. It uses port 20 and port 21. Port 20 is going to be used for the data transmission. Port 21 is going to be used for the exchange of control messages in the FTP session. But it is a reliable connection-oriented service that allows us to transfer files. Conversely, TFTP, which we see kind of at the bottom of the list here, is a trivial file transfer protocol. Notice it runs over UDP port 69. It's connectionless, and it's typically a protocol that we would use to manage our file systems on our routers and whatnot. We use TFTP to copy and move files to and from our network devices. Other protocols like SSH, Secure Shell, that is, it's not related to Telnet, but it performs a similar function as Telnet. It allows us to remotely manage a device or remotely access a device, but it includes strong authentication, and it also includes encryption. Right? SSH has an authentication and encryption component to it. So the message flow and the data flow is encrypted. Telnet, pretty much the same thing, TCP port 23, but the information is sent in the clear. All right? HTTP, you guys are familiar with what HTTP is. HTTPS is the secure version of that. Basically, it's HTTP with TLS or SSL. Typically TLS these days, but SSL as well. DNS, the domain name service, allows us to resolve human-readable names into an IP address. It says here port number is 53, but TCP and UDP. We use the UDP for standard DNS queries, you know, your client-to-server transactions. We use TCP for things like zone transfers, server-to-server communication, and so on. All right? Snmp, Simple Network Management Protocol, is just one example of a protocol that is used to manage devices. Snmp is an interesting protocol because, and we probably won't get to it in this session this week, but it provides a way for us to manage a device by either getting information from the device or pushing information to the device. We have different transactions that Snmp provides, and we use something called a management information base, or a MIB, to manage that device. A MIB is basically the structured management architecture for a particular device that allows us to walk through that device and manage it. Things like CPU process utilization, memory utilization, interface statistics, stuff like that. All right? So these are just kind of introductions to some of the applications that we see. We're going to do a little bit of a breakdown of some of these applications. I don't think it's absolutely that critical that you understand these applications in detail, but there is one, which is DHCP, that we're going to spend a little bit more time talking about. HTTP, the Hypertext Transfer Protocol, is a way for us to transfer data over a web interface. You guys know that, right? I mean, you've been working with HTTP all your life, practically. HTTP is actually a kind of a suite of protocols, if you will. I mean, it is a language. It does allow us to send and receive data. It operates, like I said, over TCP port 80. But there are many ways of transferring data over, or there's many types of data formats that you can transfer over HTTP. HTML, PHP, JSP, PL, I mean, all kinds of types of or formats of data. It's a transactional protocol, so it relies on transactional events. So almost like a get and a request and receive type of transaction. And it uses a ASCII-based context to deliver messages back and forth between the clients. If you look at an HTTP flow from a PC's perspective, you can see those transactional messages. Like I said, I'm not going to spend a lot of time talking about that protocol. This is the request response cycle that I was basically referring to before. An HTTP GET or an HTTP request is, hey, give me this information. So I go to a web server, I resolve that web server, I set up my three-way handshake, I set up my TCP session, and then I start getting information. Give me this image. Give me this web page's configuration based on text. That gets sent up to the application, and all of that data gets interpreted and the page gets rebuilt in your browser, right? So we're almost like we're decompiling a page on one side, sending it as raw data, and then we're recompiling that page on the other side based on the information that we're receiving. That's why when you open up a web page, you actually see multiple sessions established as well, because you're capturing that web information in different streams or different data flows. All right, so the client sends a request to the server receives the request, sends a response, etc. Pretty straightforward stuff. All right, web browsing is a perfect example of that. All right, another protocol is DNS. DNS is a way for us to resolve human readable names into an IPv4 address or an IPv6 address. That's at least one function of DNS. What are some other functions of DNS? Resolving mail exchangers, right? MX records, aliases for websites, like CNAME records. Of course, we have our A records and our quad A records for our actual resolution of a name to IP resolution. In IPv4, we use an A record for that. In IPv6, we use a quad A record, which kind of makes sense because IPv6 addresses are 4 times the size of a v4 address. All right? It's a database that allows us to resolve those human readable names. And it does have a very specific architecture, right? There is a hierarchy to the DNS information. But we send a DNS query for a particular name or a mail server or whatever we're trying to resolve, and then the DNS server sends a reply. They have a pretty diagram here. It says, hey, tell me who google.com is. Oh, google.com is this IP address, okay? And that's how we resolve to IP, and then we can fill out our payload information or our packet header information. Obviously, we could talk a lot more about DNS as an application. There's a lot more to it than what I'm describing. That's not really the point of this class. But one thing we will talk about in more detail is DHCP, the Dynamic Host Configuration Protocol. We know what DHCP is for. right? DHCP provides us the ability to assign addresses to clients. Not only addresses, but masks, gateways, even other parameters like a TFTP option or other options, option 66 or option 43 for maybe resolving what a wireless LAN controller is or whatever. So there's actually hundreds of different options that we can assign through DHCP. It's a transactional protocol as well. In fact, there's 4 separate transactions that take place in DHCP, not only for IPv4, but for IPv6 as well. We call it the DORA process. The DORA process, Discover, Offer, Request, Acknowledgement. And for IPv6, it's a solicit, reply, let me make sure I get this correct. Solicit, reply, request, acknowledgement. Let me make sure that's correct. Yeah, so it's actually a solicit, an advertise, a request, and reply. It's the same concept though. A solicit is like a discover, where I'm basically going out and I'm saying, hey, is there somebody out there that can give me DHCP information? Can lease me DHCP information? The advertise is like the reply, or the offer, excuse me. Yes, I'm a DHCP server, and this is what I can provide you. And then the request is like a reply in IPv4. I like what you have to offer me. Can you please now officially assign that information to me? And then the final acknowledgement, which is the reply in the case of IPv6. In the case of IPv4, it's just an acknowledgement, says, hey, yes, I have now confirmed that that address is allocated to you. You can now use that address. Come check back with me in a specific period of time based on your lease time and let me know, and I'll let you know if you can still keep using that address. All right? In general, we know what the purpose of DHCP is. We now have a kind of an understanding. We'll see it in the book as well of the different messages that go back and forth for this process. Depending on the actual DHCP server that's in use, there are 3 basic ways that you can allocate addresses. The most common is dynamic allocation. All right, this is what most people think of when they think of DHCP. Dynamic allocation is where I just generally go out and I say, hey, is there anybody out there that can provide me a DHCP? That's the first step, is the Dhcp Discover. Let me highlight that. The Dhcp Discover, which is a broadcast. It makes sense that it's a broadcast because I don't even know what network I belong to yet, right? I don't have an IP address. I don't have any presence in a network. So I can't really send a subnet directed broadcast. I can't send a unicast message to a server because I don't even know what network I belong to. So I send out this broadcast that includes my MAC address. The server, if it's listening on port 69, I was thinking if it was 68 or 69, there's boot PS and boot PC. I believe it's actually 68. Let me verify that. Yeah, 67 and 68 would be boot PS and boot PC. Boot PS port is 67, yeah. So boot PS is 67, boot C is 68. So the server is listening on port 67, the client is listening on port 68. It's a UDP-based transaction as well. But 68 is used for the client to receive the DHCP server responses. 67 is used by the server. Yeah, 69 is TFTP. So, yeah. All right. So that Discover gets sent out. The server, if it's listening on that subnet, or if it happens to get that broadcast, and we'll talk about what happens if the DHCP server is not in the same subnet as the client, because it is a broadcast, which means that it shouldn't go through a router, right? But we know that we don't put DHCP servers on every network in our topology, so there must be a way to get around that. It responds with the offer, and the offer is basically this is what I have to offer you. This is the IPv4 address. Another typo there. IPv4 address from the pool, the scope that I have defined. If this address is acceptable, if the client, oh, that's good, I like what you have to offer, then we send the request, meaning that, hey, this is the third step in the process. I'm agreeing to what you're offering me. And then finally, the server sends its final acknowledgement, which is the Dhcp Ack saying, okay, you can now start using this particular IP address. All right? That is the DORA process. Usually, typically, when DHCP addresses are given, especially if it's dynamic allocation, you're only going to get that address for a specific period of time. That's called your lease time. And usually, the client will always kind of go back after about half of the lease time has expired to see, hey, can I go ahead and renew my lease now? We don't usually wait until the lease timer expires completely before we renew the address, even though that's what the book is describing. We usually will go back and renew prior to that. The other is automatic allocation. Automatic allocation is basically exactly the same as dynamic. We're allocating an address from a pool, but there's no lease time, which means that that address, once it gets assigned to you based on your client ID information, which is typically related to your MAC address, the next time you come around and you do another Dhcp Discover, I have a database that says, oh, you're supposed to get this address. Static allocation is where you go into the Dhcp server, you define what address is going to be assigned to what client based specifically on their client ID. All right? So very, very simple protocol. There's a lot of customization that can happen with this protocol, but overall it's a simple protocol. We got the DORA process, discover, offer, request, and acknowledgement. All right? What do the payloads look like? This is the original message. This is the Dhcp Discover. Notice the source address is quad 0 because that's what the quad 0 means. I don't have an address. I am trying to establish an address. The destination address of the packet and the frame is broadcast. And the protocol is DHCP. That's the application layer protocol. The transport is actually UDP 67. Well, in this case, because this is a Discover, the source port is 68 and the destination port is 67. And then here's the reply. The source is the IP address of the DHCP server. Notice the reply is also a broadcast, and we're offering you this address. There's other things that are included in that offer, right? What is your gateway? What is your subnet mask? What is your domain name or DNS name or DNS extension? And there could be a whole bunch of other things that are offered. Then we send our request. Again, we're not using the address yet because the server hasn't acknowledged that we can. The request is actually kind of unique. First of all, let me ask you guys this question. When I send out a Discover, assuming that that Discover goes everywhere, we've configured our network to forward or to forward those Discover messages using IP helper and whatnot. Let's assume that Discover goes everywhere. Who's going to respond to that Discover? Any DHCP server. Any DHCP server could respond. So you could potentially get 3 or 4 or 5 responses. Assuming that the DHCP server has a scope that falls within the threshold that you're trying to, where you're trying to get an address for, and assuming the server has the ability to respond, it will respond. Which offer do you think the client is going to accept? If I get 4 or 5 different offers, which one do I typically accept? The first one. There is no distinction of better. You might say, well, better might be one that has a longer lease time, or better might be the one that has more options or more information. but actually the client will just accept whichever one it gets first. So the way that you can handle that is you can delay within the scope of a DHCP response, you can delay the amount of time, or you can increase the amount of time it takes for the server to respond to a request, or to a discover. All right? So notice that every transaction is broadcast-based. Every single transaction is broadcast-based. That brings up a bit of concern, doesn't it? Because we know that broadcasts do not go through routers. So does that mean DHCP does not work through a router? Natively, that's true. DHCP does not work through a router, which means you either have to have a DHCP server on every single broadcast domain in your network, or you have to have some other way of handling that broadcast traffic. All right, let's talk about that. One of the options you have is to go ahead and just set up your router as a DHCP server itself. The router can act as a client or it can act as a server. In this particular case, they're actually showing us how we're configuring our router to act as a client. It's a pretty simple concept, IP address DHCP. So when the interface is turned on, the router boots up, it's going to send out a DHCP Discover just like a client would. And then it can get an address from the DHCP server. All right. If you, once you do get an address, you can do a show IP interface brief, and you can see that the address was allocated. In this case, we were allocated 1.10, and the method of allocation was DHCP. So that's a pretty simple concept. You can set up a router as a DHCP client. Now, going back to the problem that we talked about previously, which is what happens if the DHCP server is not in a common subnet? What if the DHCP server is in my data center, or the DHCP server is in some other network location? You got the customer LAN here behind a router. That customer LAN has clients that need DHCP, but our DHCP server is somewhere in the cloud. Okay? Maybe not even directly attached to the next network, but maybe 10 or 15 hops away, who knows? Normally, the DHCP Discover that is sent from these clients here gets blocked at that router. Unless you go into that interface. This interface here would be the interface on this side. And you set up a command, IP helper-address. We're setting up, in this case, something called a DHCP relay agent. We're actually configuring the router to relay, not duplicate and pass, but relay the DHCP request. When we configure a router as a DHCP relay agent, the router actually forwards the DHCP message, but it doesn't forward it as a broadcast. It sends it as a unicast packet. So it becomes a routable packet at that point. Now, what happens when the DHCP Discover, so we send out this DHCP Discover, right, from this network. It gets converted to a unicast datagram and gets sent to the DHCP server. How does this DHCP server know what scope it needs to assign an address from? In other words, this DHCP server could be getting discovers from lots and lots of subnets. How does this DHCP server know what address scope to use? Because this interface that's doing the relaying has an IP address in that subnet, doesn't it? You guys would agree that that interface has an address that's supposed to be in that subnet, right? And when this router relays the data, there is a field within the DHCP payload that indicates who the person is that's relaying the information, which includes the IP address of that individual. So the server can say, the DHCP server can say, oh, I just got a relay request from 10.10.10.10. So I need to to reply with an address from the 10.10.10 scope. The message goes back to the router. The router then sends out the offer as if it is the DHCP server. So the clients actually don't really know that this is a relayed message. They just think it's normal DHCP. All right. Again, the book does describe the option that I was referring, option 82. That's how the server knows what scope to choose from, because option 82 allows us to identify who's relaying the data. But then the DHCP server responds to the relay agent. The relay agent strips off option 82 because it's not necessary for the client, and then it sends the response to the client. Again, in this particular case, the router is acting as a relay. It's taking those broadcast messages, it is converting them to unicast, and it's sending that information along to the destination. All right? All right. How do I configure the router as a DHCP server? What if I want the router to act as a DHCP server? We can do that by setting up a DHCP pool. And actually, it is a pretty robust feature on a router. You can actually assign, a couple of thousand addresses from a router, potentially. You can have multiple pools. The router can act as a DHCP server for multiple segments. So there is it is a pretty nice feature to have on the router. What types of environments would I typically want to configure DHCP on the router? Maybe at a branch location, a remote location in my network, right? Where I don't want DHCP traffic going over the WAN. I want to keep that DHCP traffic local. So here's an example where we've set up a router as a DHCP server for the 1.50 subnet. What you do is you create a pool, and you just give the pool a name. In this case, they called it customer. I would usually write that name in all caps because I like to see what's named versus what's not named in my config. And the names always stay in all caps, even when you type them in all caps. They kind of stand out in the config in that way. We specify the network. We can do this with a slash notation, prefix notation, default gateway, DNS server, domain name, lease time, and we can do a bunch of other things as well. We can assign options, pretty much anything that you can do in an enterprise type or a Windows-based or Linux-based DHCP server, you can do on a router. And then we have our exclusions. Now, it's interesting, the exclusions are kind of separate from the pool. This is an exclusion range. So in this particular case, we're excluding addresses 1 through 50. So if you have multiple exclusion areas, so maybe you're excluding the first 10 and you're excluding the last 10, you might have to set up multiple exclusion commands. But that excludes those addresses from being assigned or allocated. So it's kind of like we're defining our scope in this case. It's the whole subnet, but we're excluding these addresses within the subnet. All right? And then they break down the raw syntax. The lease time is in days, hours, minutes, or you could say infinite if you want to do that automatic allocation that we talked about, where there's basically no lease time. All right? As far as verification, we can use the show IP DHCP pool command. I have a feeling we're going to see something like this in our discovery. We're going to be configuring DHCP. Show IP DHCP binding shows us the binding database for the server. We can also clear that database if we need to, and so on. On a Windows platform, I can verify DHCP settings with ipconfig. I can do a release, a renew. You guys are probably familiar with that. I'm not going to go through the specific details here. By the way, if I do a release, there is a different type of DHCP message that's generated. It's an actual DHCP release message saying, I'm giving up my lease, basically. So you want to allocate this address to somebody else, go ahead. I don't need it anymore. All right? All right. So that brings us to the last part of this section here, which is Discovery 4. Let's go ahead and get into it. All right, so in this discovery, we are going to basically just take a look at some basic TCP and UDP services that are enabled on a router. Actually, Cisco routers actually have several different services enabled by default. And in fact, some of those services you may actually want to disable. Things like Telnet or DHCP and so on. There is actually a command that we can use to verify what services are running on the router. It's the show control plane open host open ports command. We see that listed right here. So if I go into router 1 and I execute that command, it shows me, well, it would show me, it doesn't look like it works on this iOS. It does not. So we'll have to rely on our output. I believe that's a GNS3 thing, but anyway, on a typical router, we could run this command, show control plane host open ports. And we can see actually that there are many different ports that are open by default. Telnet, SSH, right? SSH server, Telnet server, HTTP server, the HTTPS, and UDP port 123, which is network time protocol. I'm wondering if there is a different command we can run. Show hosts, nope, not that one. Show control plane, show open ports, nope. Let me see what version we're running here. 15.2.4 S7. Let me see if it works on the switch. Show control, no, it doesn't work. Just show controllers, which is a completely unrelated command. So unfortunately, it's not working in our iOS V environment, but you get the idea. This allows us to identify what ports are active on the device. And part of the Network Security Foundation principles that Cisco recommends is to say, let's go ahead and disable those unnecessary or unneeded ports. These ports are in the listening state, meaning that anybody could send a TCP SYN request and this router would then respond with a Syn Ack based on establishing a session to these particular ports. All right, both HTTP and HTTPS are going to use TCP, as we can see here. We also see that both them, they're both HTTP core service. To distinguish them, we identify the difference between them based on their port number. Port 80 versus port 443. All right, I'm not sure why they're listed twice. We see the foreign address is basically anybody and any port. The colon represents the port, so anybody and any port. So what they want us to do now is they want us to go ahead and go into the console of our PC, use Telnet to connect to router 1, and that may not work unless we apply a configuration, but let's give it a try, because I don't think I did put in the password. Yep, I didn't. So we're going to have to do that real quick. Just go into router 1 real quick, config T, enable secret Cisco 123. You have to have a password configured in order for us to be able to telnet to that device. So that's one of the commands that I didn't apply, but the password is Cisco 123. So just go into router 1, global config mode, enable secret Cisco 123. Then we should be able to telnet to that device. We'll have to do it on the VTY lines as well. So line VTY04, password Cisco 123. All right. So now I should be able to telnet. Yep, Cisco 123, enable Cisco 123. So now I have an active telnet session to router 1 from PC 1. So I go back to the, if I was able to run the command, I'd go back to router 1 and I use the show control plane host open ports, and I can actually see that active session established. This is very similar to the netstat command. Remember we talked about the netstat command on day number 1 on a Windows machine or a Linux machine to see what kind of active sessions we have established on our Windows machine. We use netstat. Well, this show control plane host open ports is a very similar command. All right. So I was able to find a command, show TCP brief all, and that shows me my TCP session. This is the destination or the local address and the port number. So this is my port 23 for Telnet. This is the foreign host, and this is the ephemeral port that they're using to connect to me, and the current state is established. Let me try show UDP as well. No, that one doesn't work. Show TCP brief. Yeah, I wonder if there was a way to see the listening ports. I was just trying to see if there was a way to see the listening ports. Doesn't appear to be, but this does at least show us our established connections. It doesn't give us the control plane open ports command, but we can at least see that active session. All right. And in our case, in this particular case, the ephemeral port is 14044, but the key is that the session is established, right? Meaning that we went through the TCP three-way handshake. We've established that connection between the PC1 and the router. So access the console of PC2 now. So access the console of PC2 and telnet to router 1. And we should see that other connection as well. Wrong window. So PC2, telnet 10.1, 10.10.1.1, Cisco 123, Cisco 123. And now if I go back to my router, I could do it from that window, and I do show TCP brief all. Now I see the second session established, and that particular client happened to use 43316 as its ephemeral port, but again, port 23. Pretty basic concept. All right. Again, if I was able to run the show control plane open ports, I would see the session listed there as well. All right, this TCP session established. Return to the PC1 and type exit to close the session. Exit to close the session. Obviously, in that case, that's going to go away. And close the session from PC2 as well. So go to PC2, exit. And now if I go back to router 1, I should, yeah, we're in a wait state. So what happened in this case is the TCP session didn't close gracefully. In other words, by typing exit, it didn't instruct the router that I want to finish the TCP session. Meaning that we basically have this zombie connection now, what we call a TCP zombie connection. Eventually it will time out. I can't remember what the timeout period is for a TCP zombie connection, but or that dead connection, but it will eventually time out. Okay? So if I wanted to disable services, there's several ways to disable services. For example, if I wanted to disable the HTTP service, I simply say no IP HTTP server, and that disables that service. I could say no IP HTTP secure server. I believe it's secure-server, and that disables 443. No NTP disables port 123, and so on. So you can turn on services, you can turn off services. by executing those commands. They had us in the exercise disable HTTP and then go back and do a show control plane host open ports to see that that HTTP service is disabled and only HTTPS is enabled. All right? And that is pretty much the entire discovery. It's a pretty basic discovery. There is one other thing that I do want to show you guys, though, that you may not be aware exists. It's a little bit beyond the scope of this lab, but it's also kind of related to this particular lab. So let me do a term length of 0 and do a show run. And I'm going to grab the configuration of this router. I'm just going to copy the whole config. All right. And I'm going to open up an application called the Cisco configuration or CLI Analyzer. This is a free application that you can download from cisco.com. You have to have a CCO account, and I believe you have to have at least one service contract open. Don't tell me it's not going to open. Dang it. CLI Analyzer open. Let me go ahead and get it again here. So if you go to cisco.com, I actually want to show you this tool because I think it's a really, really useful tool. And you search for Cisco CLI Analyzer. Under the Tools section, you can download this tool, and what it allows you to do is paste in your configuration, and it also analyzes debugs and other types of outputs, but it analyzes your configuration, and it gives you recommendations on how to secure your platform. So it will tell you this service is enabled, this service is enabled, you need to do this to disable this particular service, and so on. It's a very, very useful tool. I thought I had already had it installed. Let me try and start it from my other screen here. Cisco CLI Analyzer. But for some reason, the app isn't launching here. So wait for this to load. Oh, it did load. Okay, good. There we go. So that's how you find it on cisco.com. But let me go ahead and load up the tool. And it, like I said, it might require that you have a service contract to run it. But it's a really, really simple tool to use. You have to log in with your account. Let me go ahead and log in. Let me think, which account? I think I'll use this one. No, I don't want to upgrade. And then what you would do is you would do file analysis, and you can literally just paste in your config and do start analysis, and it will generate the results, and it gives you essentially all kinds of different options about your config. So it says here, let me see, 5 results. Improve the security posture of your device by disabling Telnet. And then it says, it describes how you can do that. The MOP service is enabled. It tells you what the MOP service is. Maybe you want to disable that. IP BootP services are enabled, so DHCP services. Found missing some of the router security best practices. Failed login attempt notification should be configured. Enable NTP authentication, password minimum length check, and these are actually clickable links, and then it will take you, usually it works, to the document that describes how to set up that particular feature. So it's a pretty useful tool for securing your platform, and it is kind of related to what we're talking about. We were talking about open ports. There's no authoritative time source. We don't have the HSEC license installed. That's the security license. Found missing router operations best practices, securing the memory, critical memory, and so on. So this is kind of a way to baseline, if you will, the overall configuration. You can post debugs as well. It doesn't have to be a config, because a lot of times the debugs are somewhat cryptic, especially if you're doing like voice traces and stuff, and they'll have a bunch of codes in there. You can paste that in, and it will analyze that debug for you, and based on those codes, it will give you information about that particular error message or that particular output. So kind of a very useful tool. It used to be, you didn't used to have to download a separate application for it, but Cisco, I think, got a lot of flack because you were actually pasting the information to their website. And people were like, well, I don't really want to provide my information out there into the public. So the CLI Analyzer, okay? All right, we'll wrap up this discovery. We'll wrap up this section. We'll see you guys in the next lesson.